Okay. Thanks for coming. I will start by repeating myself so that we know what we're going to do today. But what I want to do essentially today is to prove the last theorem that we showed yesterday. So Cilanne-Boulet's 2006 theorem, which gives two explicit formulas for generating function for partitions with colors, with 4 colors. But let's do some repetition. So this symbol A base q sub infinity is an infinite product. It is the product of the form 1 minus a q to the I, and I starts from 0 goes to infinity. I don't care about conversion, so you can read it as it starts at 1 minus a, it starts at this point a. The steps are of size q, and you have infinitely many of these products, right? And using this, we generate a lot of generating functions. I will write them in a second too. But when we have way too many of these products, and it happens that we see similar products all the time, we start to compress things. So if you see me writing A1, then A2, then AK, base Q, sub n or sub infinity, this would mean I'm actually taking a product of each and every Q per hammer. And that is this first one with the base Q, and the sub in this infinity, then the next one with the same base q with sub in this infinity, k, q, sub infinity. So if I have too many of these products with the same base and with the same number of products, I would just compress them. Which Khan, for example, did it by accident, like without even noticing in his talk yesterday. Because you just get used to this. Okay? So let's see a couple of examples that we did yesterday, how we use them in generating functions. So one example was 1 over q infinity is the generating function for the number of partitions, or for the partitions, however you want to imagine this, for the number of partitions, let me write it that way, of partitions. And that is the only thing, there are no restrictions. And here's a good indication. Whenever you see something in the denominator, whenever you have a reciprocal product, you are dealing with the geometric series. So you have unrestricted number of parts, so things can repeat. And if you don't want things to repeat, you just put them in the numerator. You don't introduce a denominator. So minus q infinity, which was also something that we saw, is the generating function for the number of partitions again, but this time into distinct parts. Into distinct parts. So things do not repeat. All right. Good. Then we said in AQ sub infinity, we said this is the starting point, there is the step, there is the number of products. So you can just go in larger steps and you can start at some other point than just starting at q. So for example, you can start at q squared and go with steps of 3 of infinity. If you were to look at the product, this would just look like 1 minus q squared, so plus q squared. Then the next one would be 1 plus q squared, then 1 step, so q5. 1 plus q8, so on and so forth. So you will be dealing with 2 modulo 3 parts. So character doesn't change, but the starting point and the modulus changes. So this is the generating function for, I'm basically going to repeat what I said here, but I will add one more condition. Generating function for the number of partitions into, this time I have 2 modulo 3 distinct parts. 2 modulo 3 distinct parts. This is the new addition to the clause. Where was it here? Like in the last example, it was actually there. It was 1 modulo 1 distinct parts. So it didn't matter. It was just the normal thing. We started from 1, we went all the way. So you divide anything with 1, you would get a 0 modulo 1, but I mean 1 modulo 1, 0 modulo 1, the same thing. Right? And these type of steps are important, these are useful, because you can use these things to sift your partition into finer pieces and maybe use some pieces that you like and not use some pieces that you want to avoid. For example, let's take one example partition. I don't know. Let's take maybe the large example that I want to do. After all, I will need to draw it at some point. So 14, 14, 12, 11, 8, 4, 3. You can tell I'm not excited to draw the Ferris diagram of this, which I will. So we have this partition. We know this is generated by this generating function. So among the combinations of things, one of them is generating this guy. But maybe we can do some refining at first. Maybe we can just do some bijective sifting as we like, dissect it a little bit, and look at the pieces of look at the pieces that would generate the sifts, the pieces. One example is, I can take all the even parts of this partition, put it in one basket. I can take all the odd parts in this partition, put it in another basket. And that would be bijective, right? I mean, there wouldn't be any ambiguity of what is even, what is odd, or I wouldn't be losing so much information. Let's try it. So I will split this into two pieces. I will put all the even parts in the first basket. I will put all the odd parts in the second basket. So 14 is even. I'll keep it that way. 14 is even. I will keep it here. It's also an even part. Then 12 is even. That's good. 8 is there. Then 4. 3 is odd, so we don't use it. 11 is odd, so it goes in the second basket. And 3 is odd. It goes in the second basket. So I sifted in two things. You can notice that this is already two partitions. So this is a partition itself. That is also a partition itself, right? And this is a partition in even parts. So what do you think? If I want to generate partitions only using even parts, what should be the generating function that counts this thing is? Like that should be. I should only have like 0 modulo 2 parts, right? So you can just say, oh, this one, the first one, is the thing is generated by, maybe I should write it here. This thing is generated by things with, you start with 2, because you need to start with an even number, and you go with steps of 2. So you hit every even number, sub infinity, right? So among all the combinations, one of the combinations is this partition into even parts. And this guy, you need to start with odd numbers. You need to use only odd numbers. So I got to start with the first odd number that I want to start with. I mean, the first ever odd number, positive odd number. Otherwise, it doesn't even make sense to say the first one. The first positive odd number is 1. So I should start with Q1, right? And then you go with steps of 2 so that you hit 1, 3, 5, all the odd numbers. Cool. And one combination is that 11, 3 among this, right? Well, the good thing is, in probability, in partition theory, in combinatorics, in logic, if two things are disjoint, you can just multiply the outcome. It's like you have two independent events, probabilities, you multiply the things. You have two independent partitions, generating functions. When you want to put them together, you multiply their generating functions. You look through all the combinations. So what I'm saying is, the partitions into even parts and partitions into odd parts are completely disjoint. There's not even going to be one element that matches, right? So if I were to put their generating functions together for the even parts and the odd parts, it will be the generating function for the partitions, period. And how can we see that? Like, this is just a dissection, and it's a nice dissection. But how can we see that? Here we had 1 modulo 1 part, so we were starting from 1, hitting the next one is 2, then 3, then 4. Over here we're just jumping from one to another. So 1 is here, 2 is there, 3 is here, 4 is there, right? So it's literally just a dissection. In the same way, you can write it in, for example, modulo 3. So you can say, oh, 1 modulo 1 is the same thing as I have 1 modulo 1 parts, 1 modulo 3 parts, 1 modulo 2 parts. Apologies, I want to split it in 3, the modulo 3. So if you want to do that, you can say, I will have 1 modulo 3 parts, I will have 2 modulo 3 parts, and I will have 3 modulo 3 parts. So that's the basic dissection. And that would, if you want to split it, it would look like q squared, q cubed, base q cubed sub infinity. And just so I'm using the abbreviation as well, right? I have 3 products. Basically, the first one is going to be 1 modulo 3 parts, the second one 2 modulo 3 parts, the third one 3 modulo 3 parts. And these 3 groups, these 3 generating functions are disjoint. So we can put them together with multiplication. Just a way of saying that we can sift things, we can combine things. So you can read them backwards. You can combine them, you can sift them as you like. And this also helps us to say, if I want to avoid one group of numbers, I might as well get rid of its generating function in this construction, and then I won't have them. For example, let's say I want to count the partitions, but I never want to use 2 modulo 3 parts. Right? I never want to encounter a part that might be 2 or 5 or whatnot. Then I know the generating function for 2 modulo 3 parts is q2 q cube sub infinity. So if I don't want it, I will hit my generating function with the multiplicative inverse of this. So I just cancel it. This is less combinatorial. There's a cancellation. We don't know how that cancellation works in the generating function sense. But I have a generating function. I don't want to see any 2 modulo 3 parts. Just hit it with its inverse. Okay. So just some recap and just a couple of ideas that we can dissect things. We can put them together. We can cancel some classes if we don't want them for now. Now, the theorem that we want to prove today has nothing to do with these things. It had like A, B, C, Ds and everything. So let me just remind you that I want to draw the Ferris diagram of this guy. And I'm still not excited to draw the Ferris diagram of this guy. So it's a partition. Largest part is 14. I think it's a partition of 66 if I edit that correctly the first time. And it has 7 parts. And the Ferris diagram looks like this. So the first row is going to have 14 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, good. The second one has another 14 boxes. Okay, then 12, so here. Then 11, 3, 9, 10, 11, 8. So this was 11, this must be 8. 7, 8, good. 4 and 8, 3. Cool. Now, this is the Ferris diagram of this guy. The first row has 14 boxes to indicate that the largest part is 14. The second one has 14 boxes. The last one has 3 boxes to indicate that the last part is 3, so on and so forth. Now, in the generating functions in the classical sense, I said we fill these boxes with q's, we multiply them all. And that becomes a size, q to the power size, and that contributes to the generating function. We then said, Richard Stanley and his student Cilanne Boulet had the idea, maybe we shouldn't do it that way, but we should just color them A, B, A, B, A, B in the odd index rows. A, B, A, B, A, B, A, B, A, B, A, and C, D, C, D, C, D, alternating C's and D's in the even index rows. So in the second row, in the fourth row, C, D, 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 C, and C, D, C, D. Cool, great. No. And yeah, if A, B, C, D are all Q's, we are back in the original case, which we should check in a second. But if we want to deal with this general case, they said that we can actually write the generating function of these things. Just define a weight of a partition. So define a weight of any given partition pi, weight of A, B, C, D, I should say, maybe even. That is A to the number of A's in the thing, B to the number of B's, C to the number of C's in the Ferris diagram, D to the number of D's in the Ferris diagram. So for this example, it is going to be a little bit messy, but let's count it. 4 in this column, 4 in this column, 8 A's, 11 A's, 14 A's, 16, 18, 19 A's. So this example, the weight of this partition is the weight of this guy. Is going to be A to 19. B is going to be 18, I guess. Correct me if I'm wrong. The trick that I'm using is every A is followed by a B, except for this last guy. So they must have almost the same number, but one is missing. C, every A has a C underneath, except for 1, 2, 3, and 4. So that C is going to be 15, and D, I will have every B has a D underneath except for 4, so it is D of 14. So when you add it up, is it 66? Is it? I don't know. I'm not doing the math. If it is, then it is. If it's not, I made a mistake. Maybe in the partition, maybe in something else. Anyway, so we want to find the generating function of this. We want to find the formula for the generating function of this. And we know people actually found the formula for the generating function of this. And let's write them. Good. So Theorem, Boulet, and it is 06. The first one is P of A, B, C, D. And this is the generating function for ordinary partitions, any partition that you can think of, but instead of counting the size that we were doing before, this time we have the weights of pi. So we have A, B, C, D combinations inside. Okay? And this one has a product formula. It is minus A. Then I'm putting a comma, not a semicolon, so I have multiple products. The next thing is minus A, B, C. And semicolon, capital Q. I will define capital Q. Let capital Q to be A, B, C, D. A times B times C times D is capital Q. So on the top I have minus A, B, C. I will explain what they are, but they're going to be quite natural. And on the bottom I have AB, AC, then a capital Q, then a capital Q sub infinity. So this generating function at this generality with A, B, C, D has a product formula. Great. The second one is psi of A, B, C, D. And this is pi in D. We defined them yesterday, so P is the set of all the partitions, D is the set of partitions into distinct parts. And instead of the size of Q again, instead of having the Q's, I have the colors. I'm counting them with the weights. So for example, that example that we have is being counted for the first one, but not for the second one, right? I mean, that has repetition. And here, this one also has a product representation. And that one is quite similar. The top part is the same, minus A, B, C, base Q, sub infinity. So this is a semicolon, that is a comma. So I have two products here actually. And on the bottom, I only have one product, and that is AC. I always need to think if it's AB or AC. I know it's one of them, but it's AC. No, I'm wrong. It is AB. I usually get it right. This time when I'm bragging, it is wrong, but it's AB. Yeah. Perfect. Now, well, first off, this is a generalization of the generating functions that we have seen. Or so we are saying. We know that when A, B, C, D are all Q's, we should get these generating functions, where we count the number of partitions itself and it's Q, Q infinity, or when we're counting the partitions in the distinct parts. One of the two, right? So to get ourselves convinced and to get a little bit more confident with that, maybe we should just plug in A, B, C, D to be all Q's and see if it really becomes those things. That's the first thing to check. If it is not, maybe I should just change my claim of AB to an AC. Who knows? I will need this Ferris diagram in a second. So let's take this and let's do it here. Now, if I were to plug in A, B, C, D to be all be Q's, the weight A to the number of A's, B to the number of B's, C to the number of C's, and D to the number of D's in the Ferris diagram would become Q to the number of all the boxes. So it's Q to the size. So that portion is not too bad. So just to try, so let A equals B equals C equals D equals Q. So I want to drop down to what we have already proven. And this P of Q, 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 Q is now the generating function of all the partitions from the set of partitions. And instead of the weight, I say that when we have Q, 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 Q here, it is the number of boxes, which is the size of Q. So in an abstract sense, at least we know that this should count what it is. Now we will check the formula. And we haven't proven the formula, so maybe I should even put a question mark here, right? Because that's a theorem, but we haven't proved it. We haven't seen the proof for ourselves yet. So when I plug in Q, I will have a minus Q here. I will have a minus Q cube, and the capital Q will become Q to the power 4 sub infinity, right? On the bottom, I will have Q to the power 2, which is AB. Q times Q is Q squared. Q to the power 2, Q times Q is Q squared, and then Q to the power 4 is Q to the power 4 sub infinity. Cool. Now we have different pieces, we have some repetition and stuff like that, but let's pick and choose. Let's do some cherry picking, whatever we like, and let's try to combine them. For example, I want to combine this top portion. I have 1 modulo 4 parts and 3 modulo 4 parts. Can I compress it in some sense? It is all the odds, right? I mean, an odd part is either 1 modulo 4 or 3 modulo 4. You can just combine them, and as an odd, it will be 1 modulo 2. So that infinite product is the same thing as minus Q1 and go in steps with 2. So this one is going from 1, 5, 1, 5, 9, 13, whatnot, and this one is going like 3, 7, and whatnot. So I'm just alternating now. So I'm just going 1, 3, 5, so on and so forth. So I'm just combining. What about these two? So I have Q squared here, Q4 here, and the base is Q4. I have 2 modulo 4 parts, 4 modulo 4 parts. So this and that, or the other 2 and that, one of them. So I can combine it again. That is all the evens. Q squared sub infinity, right? So 2 modulo 4 parts, 4 modulo 4 parts is the same as 2 modulo 2 parts. And this one is left, so I will keep it. Q2, Q4 sub infinity. Okay. Now what is next to do? What do you think? If this were to be the generating function that I know, there shouldn't be anything in the numerator. So I should somehow cancel that thing in the numerator. Right? Maybe we should resort to some other trick from our high school algebra. High school algebra like backgrounds, right? We have x squared minus y squared is equal to x minus y and x plus y. Good enough? Right? I will even say we have 1 squared is 1 minus y, 1 plus y, because I mean, we always have the first thing to be 1 anyway, so who cares? Well, this is squares. It's good. I can split it if I want to. This is also squares. This is 4. It's also an even number. It's 2 to the power 2. right? So which one should I split into two pieces so that it would cancel the top one? The right one. So if I were to split this, let's look at the terms here. Let's look at the, ooh, I lost my microphone. And I'm definitely going to paint myself, but it's okay. All right, the first element here is 1 minus q squared, right? If I were to split this into two using that formula, I would have 1 minus q and a 1 plus q. Good. The next term here is 1 minus q6. So that would split into 1 minus q cubed, 1 plus q cubed. Then I have 1 minus q10. So 1 minus q5, 1 plus q5. So it just splits into two pieces, two pieces, two pieces. Now let's regroup them, but regroup only the things with the negative sign in the middle and regroup the things with the plus sign in the middle. So if I were to combine all the things with the negative sign in the middle, I start with q to the power 1. So my starting point should be q to the power 1. And q per hammer already comes with the negative in the middle, so I don't have an extra sign. It is just the q1. And what is my step size? I start with q to the 1. The next step is q to the 3. So my step size is 2. I just jump 2 steps ahead. Then another 2 steps ahead. Right? So it is q1 q squared sub infinity. This is an infinite product. It just goes on. And the other ones, I again started with q to the power 1, but now I have a positive, so I should pick a negative in the middle. So it just makes that my q per hammer definition's middle sign to be positive. And the step size is again the same. It's q cubed, q5, so it is q squared sub infinity. Like you see, this guy is apparently that in the denominator, it is q squared q1 q squared sub infinity, negative q1 q squared sub infinity. But this term is the term that I want to cancel up on the top. Oh, great. So we have that cancellation for us. Perfect. So we got rid of the thing on the numerator. So numerator is 1 now. And I need one more trick. I have q squared sub infinity, and I have a q1 q squared sub infinity. Can everyone now see that this is q sub infinity? It is 1 modulo 2 parts, 2 modulo 2 parts. So I'm actually hitting every part that I need. So I'll just erase that, or I will write it with color that this is the same as q sub infinity. So this is literally what we were looking for, yeah. When we plug in a, b, c, d to be q, we end up with the generating function for the number of partitions. Should we do the same trick for the next guy? We can do it again. It's fine, it doesn't take too long either, and it's good practice. And we already did the trick, so who cares? And this time we are expecting to see negative q sub infinity, right? We will do the cancellations. We will be left with negative q infinity in the numerator. So let's do that. Let's build some confidence in this theorem before we actually prove it. So let's believe the theorem first before we prove it. And this is the generating function for the partitions into distinct parts. And I'm grouping them with respect to their sizes. So I group them with respect to their sizes. And this time, from the formula that we haven't proven yet, it is minus q cubed q4 sub infinity divided by q squared q4 sub infinity. Ooh. Now, let's see. We did most of the dirty work. So this guy becomes like 1, 3, mod 4 is 1, mod 2, and the negative sign stays the same. And in the denominator, I have q squared q4 sub infinity. And I want to get rid of this time. So I should somehow cancel that. And what I need to, and the outcome that I'm looking for is minus q infinity after all. This is the end goal that I want to see. What I need is Euler's theorem. But I don't want to say that I need the Euler's theorem. I just want to somehow trick you into thinking that I'm doing something new. But I actually have odd parts in the denominator, but they're all like counted twice almost, doubled up. I just want to go back to the distinct version. So let's cancel that. For this, I would need to have a negative q squared here. Good. For me to get that, I would need Q4. Would that work? Yes. Okay, good. So let's do the trickery. I multiply the top with Q4 sub-infinity and divide the same factor with Q4. So I don't change anything. Trickery. I just found out that I need to divide it with 1. Multiply it with 1, this term. Q4 divided by Q4, the same thing. On the bottom, I can combine these two terms. I have Q squared Q4. So it is 2 modulo 4 modulo 4, it is 2 modulo 2, right? I mean, I'm doing exactly the same tricks that we talked about. So on the bottom, I have Q2 sub infinity. On the top, now, the odd portion I want to keep anyway. So this distinct portion, minus Q squared sub infinity, I want to keep it. But I want to split the other one. And how is the split going to go? It's just going to be the same deal. The numbers are going to halve. One of them is going to be positive, one of them is going to be negative. So Q4 will become a negative Q squared, which is the one with the negative, and a Q squared sub infinity. Is that okay? Perfect. Then the Q squared I have in the denominator, Q squared, they cancel out. I have 1 modulo 2 parts in distinct form, 2 modulo 2 forms distinct. Combine them together. You get negative Q sub infinity. Perfect. So yeah, it also fits, apparently this theorem, when we plug in A, B, C, D to be Q's, it also fits what we have learned so far. So now we have more confidence in the theorem, at the very least. At least when we drop down the dimension, it goes to the places which we have already proven. 10, 40, okay. So let's try to prove this. I will try to take things out of this partition first in a bijective manner and dissect it. Then look at the generating function for these pieces, and once I stitch it together, they're going to be these products. Okay, that's the idea. And the first term that I want to dissect, in reality, is this AB sub Q in the denominator. For that, given any partition and its Ferris diagram that you can draw, starting from just looking at this thing, can I find all the odd height columns? You get a partition, you're looking at it. Can you, by just checking it, identify which columns in the Ferris diagram have an odd height? Like for example, this guy, does this column have an odd height? No, this has an height of 2, right? I mean, there are 2 boxes underneath. What about that guy? So we should be able to identify which columns have odd height and which columns have even height. That is nothing really special.
Can't have the same color if it's on.
What is it? Sorry?
Can't have the same color if it's on.
They would end at the same color if it's odd. Yes, thank you. Thank you. I was not thinking that I actually colored them. Yes. You start with the red color. If it ends with the red color, that means that you have one more red than blue, so it would have an odd number of height, right? And once I notice which columns are of odd height, can I figure out how many of them there are? So for this column size, like column of height 5, there are 4 of those columns, right? So it's not magic, it's super simple. You get one example, you find the odd heights, you can find how many there are. And if that's the case, can I combine any even length odd heights? So whenever I see an odd height, I will check if there are 2 of them right next to each other, and if so, I will group them. Just somehow color them. Would that be possible? I think it is, right? Let's start from the left and go to the right. Even height column, I don't care. Even height column, I don't care. Odd height column, but there's one of them. I'm not going to do anything with that. Even height column, I don't care. Even height, I don't care. Odd height, I do care. Odd height, oh, I have two of them. So let me just group them first. Okay. Odd height again. Odd height again. Oh, there are two of them. I will group it again. Fine. Even height, I don't care. Odd height, I do care. And there are two of them. So let me group it again. And another odd height, but it doesn't have its pair, so I'm going to stop. So we have identified which columns have odd height and which one of them comes with their pairs. Okay? Now the next question, can I take it out? And if I take it out, this is a bijective change. Is it a reversible change? Would you mind if I drove these out, which would eliminate these yellow boxes in the partition? And I will write it on the side. Now, two questions we should ask. What is left? Whatever is left, is it still a partition? If I were to ignore all the yellow boxes, whatever is left should still have that vague triangular shape, and it's still a partition, right? And whatever I take out, is that a partition? Like, so something that we know how to play with? Maybe not, we gotta be careful about that. Or at least maybe it's not fitting our rules yet. We gotta be careful about that. And the third thing is it a bijective change? So is it reversible? Or am I like damaging my information so much that I cannot reverse it? Like there are two different sources that can come to the same issue. The last thing, I don't think it is that big of a deal. We know the heights, you can just push them directly into the partition. But here, when you take it out, yeah, I mean, whatever is left is going to be a partition. It's also not an issue, but if you look at the yellow boxes, like I started a B instead of an A this time. Maybe it's not great. So BA, then if I were to directly use it, it would be an AB. So it is not in my original coloring, right? But after all, let's say we can do it, and I will do it in a second. Whatever is left would be, there's one piece which doesn't have those two-bit odd height columns. So I have this. I have this column, then I have that. So I'm really taking out the yellow boxes now. So this is that. Then I have here 3 of them. Boop, boop, and this and that. Okay. And in the outcome, I can still write like A's and B's and stuff like that. And this is going to work. That is something that I should claim. And more so, this one is not going to have an even width odd height column because I took them out. Cool. Now, if you do the coloring, if you ignore the yellow boxes, you would see that AB, the coloring still works. So I have an A on what is left, then a B, and what is left? A. Oh, no, this one is gone. A and a B and an A and a B and an A and a B. So I didn't break my pattern. Cool. So this still has that same pattern of AB, 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 and CD, CD, CD. So this portion is actually good. It's working out. In the portion that I'm taking out, this even width odd height columns, I may have the issue that some of them come with BAs. And then the next one is AB, so I'm having 2 A's coming together, although the original thing was AB, 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 right? Now I will make another bijective change. If you ever see a column of this form when you have B and A, just flip it, right? Just change the order. It is fine. So we have, this is one piece of that, what is taken out, and the second piece is that box, then this box, and here is AB, AB, and 4 of them on top. 1, 2, 3, 4. Oop. Oop. And here it is. 1, 2, 3, 4. So let me start using this capital Q even. A capital Q is a 2x2 box. So I have one capital Q, another capital Q, another capital Q, and an AB. Whenever I need to switch B and A, I'll be easygoing, I will just switch it. And whenever I have an ABCD box, I will just call it a Q. Now, let's deal with at least a generating function of one portion. What do you think? What would be the generating function for that guy? My step sizes are all q's, so this time I'm like working in conjugate almost. I'm building columns. My step sizes are always q's. I'm adding those 2 by 2 boxes. But my starting point is AB. So I get an AB, which has the 2 boxes right next to each other. Then I'm adding q's on top of that, right? So the generating function is going to be of the form AB and a q sub infinity. But should I put a negative? Is it in distinct parts, or should I put it in the reciprocal? Because it can repeat itself. There are repeats. There are repeats, right? I mean, this AB columns can come with the same height many times. Like, for example, we have 2 of them. So this should come in like that. So at least one piece of that, now we have identified. We pulled this partition from any partition that we can start with, and we know the generating function of that. Cool. Now we need to convince ourselves that the generating function for these things, whatever they might be, is the rest of it. So we just got rid of one of them. Now we got to decide what is happening with the rest of them. And great.
Sorry,
yeah, please.
Why does it end with AB on the right when it ended with BA on the left?
So whenever you need to switch the order here, you can actually pull a BA column, right? And when you reconstruct it, it might not be working out. You might be getting BAAB. But whenever you can, it's just whenever you need, it is bijective. You can just switch the columns, the order of columns to fit your coloring again. And when you're putting it back, if you need to put it right next to an A, you can switch it back again and put it correctly. It is bijective over there. No, not a problem. Okay. Well, would you believe me? Although we have only covered this portion of this generating function, would you believe me? We did the hard work. We did most of the hard work. The rest is going to be quite easy. We just need to identify what is this partition, or what property this guy has. And the property this guy has is, this is a partition where from the odd index part to the following even index part, the gap is no more than 1. Like never more than 1. The gap from the odd index part to the following even index, the gap here is 0. The next odd index to the even index part, the gap is 1. The odd index to the even index, the gap is 0. Odd index to the non-existent even index part, the gap is 1. So we dissected our partition into 2 pieces. One piece is like this odd height even width columns. And another set, let me call it R. And that is, let R be the set of partitions pi, which is lambda 1, lambda 2, blah, 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 such that lambda 2i plus 2i plus 1 minus lambda 2, so lambda 1, 2i minus 1, lambda 1 minus lambda 2 is less than or equal to 1. And now I need the generating function for these r's. So now I'm after this generating function. This weighted generating function for partitions in R. What is that? Great, right? I mean, after all, we have one property which is from an odd index part to the even index part, the gap is not growing. Because all those gaps were introduced by the odd height columns, and I took them out. Are you convinced by this? Is that okay? So let's dissect it. Now, let's say you got a partition from the set R. Some partition you got from the set R that looks like so many Q's and Q's and Q's and Q's. And it still has that vague shape, but this time it is just the boxes are Q's and Q's and Q's. Q's and Q's, this capital Q's like A, B, C, D boxes. What can happen at the very end? Let's focus on what can be at the very end. And we have examples over there. One ending might be that you have an A and you have the next ending to be C, right? You have too many Q's and Q's and Q's and Q's and it ends with an A and C. Just a possibility. Now I'm looking row by row, right? This is one possible ending. What is another possible ending? Another possible ending is it just goes and goes and goes and it ends with a Q. It just ends. So A, B, C, D, done, right? Another possibility is that you have one A. So you go and go and go, you have one Q and then an A. Still, the odd index to even index, the gap is exactly 1. There's one more ending. Can anyone think of that?
We can have ABC.
Yeah. Another possibility is just like this triangle. Maybe you have a lot of Q's and Q's and Q's, and then you have an A, B, and a C. So we're still micromanaging, but at almost like a macro level, one level higher. Okay, cool. So now we know all the possible 4 endings, and there's no other ending, is my claim. Please convince yourself of that, because the gap is at most 1. Right? It is either 0 gap, or it is 1 gap, from the odd index to the even index. Like this gap, here to there, might be huge. Like nobody cares about that. It's just from even index to the next odd index, it can be a huge gap. But from the odd index to the even index, following even index, the gap is at most 1. Great. Now let's identify what type of endings can repeat itself and what type of endings should appear at most 1 time. Can I have another copy of this on top of it or below that, and would it still keep that vague triangular shape? Would it still be a partition? This was literally a trial and error. If I had another row of the same thing, would it still be a partition? Right?
AB or AC?
AC, it should be. It will still be a partition. So you can stack up these AC endings. AC endings can repeat themselves. So when I write them in the generating function, I will put them in the denominator. There will be a reciprocal thing. What about the Q endings? What about the full box endings? Can they repeat themselves again? What do you think? Cool. So Q's can also repeat. So repeat, non-repeat. So Q, 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 all the way, and an AC can repeat itself. We said that. We can put many of them. And there is still a partition. You're not creating this dent. It's still that triangular shape and no dent. And we also have this Q, 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 full Q at the end. These can repeat itself. So the 2 scenarios, they can repeat, and non-repeats. So if you start have too many Q's and an A, this cannot repeat itself. Because if you were to put another one of them, you just created a dent. And that is breaking the order for partitions. It's not non-increasing anymore, right? So, okay, this ending cannot happen. Fine. So this is a non-repeating portion. And I believe this one is also a non-repeating bar, ABC, with a lot of Q's, the full 2x2 boxes. Now, the last thing to say is, okay, we have identified 4 different endings. We have identified which one can repeat and stack up on each other, and which ones cannot stack up on each other. The last thing to say is, when we combine terms from these 4 endings individually, can we combine them together in harmony so that their generating functions will be coming from different distinct sources, and I will just multiply their generating functions and we're good. Because if it doesn't, if like 2 different settings can create the same outcome, then I might need an inclusion-exclusion type argument. But somehow I need to say that these things can be always combined. Like give me some pieces of that, some pieces of this, just like Legos. Some pieces of that, some pieces of this, some of that, some of this. I would be able to put them together in a unique way. And that outcome can only happen from that combination. It's not that bad, just like Legos. So whenever you have an ABC outcome, right? If you have an AC outcome with that, with the same size, just put the ACs under them. If you need to flip the order, flip the order. It is fine by me as well. But you won't need to flip the order this time. And if this A comes with those two combinations, put it way underneath. So this can go under that, it's okay, right? If I were to put that next guy, this would be okay. So on top, put the ABC ending, put AC endings as many as you need in the middle, and put the A ending at the end. I'm just working in 2 rows, so I can just somehow dissect them. And whenever you have like the Q's, just put them wherever they go, under this A, right? I mean, there might be some full Q endings here. And can I make whatever the outcome of this combination of 4 things with a different combination of 4 things? The answer is no, I cannot, because I'm always working with like 2 rows at a time. So you always start from the top down, you dissect it. You just take the first 2 rows, you already know where it's coming from, you already know there's one source that it can come from. Then the second 2, you already know where it's coming from, you know there's only one source. It's just the ending defines what the source is. Okay? So there are 4 endings. No combination of any other 2 is making one of them. Like what I'm trying to say is like you cannot take some of these and that and make an ending that looks like this one. Like the ABC ending can only come from the ABC construction. Because these 2 won't have the C. Or these 2 won't have the B. Or if you use the Q, you cannot chip away the D so that you can get the like ABC ending. Cool. So many words. But after all, I'm just saying that there are 4 pieces, they're disjoint, and I can always, given any partition, I can always dissect it. And let me dissect it for you. This was the outcome. Let me dissect it for you. The first 2 rows, bam, dissected. So this is a Q, 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 Q. So this is one of those endings. Fine. Another 2 rows, Q, Q, A, B, C. That's one of those. And I know this is not going to repeat at all. And another one, this is just that. Q, fine, one of these endings again. And A, apparently this was that. Right? Given any partition, you can directly dissect it. So, and it's unique, and it's bijective, it's reversible, all that good stuff. Now let's move to the generating functions. Generating function for that is AC is the starting point. Then you take steps of capital Q. And they can repeat. And I don't care about the bound on the side, so I'm just keeping that infinity. They can repeat, so I will put it in the denominator. This guy, it is Q, Q. You start with size full box Q. Steps are Q. And it is also repeating, so Q, Q sub infinity in denominator. This guy, it doesn't repeat. The starting is A, but it's distinct, so I will put it up top, minus A, base Q sub infinity. And there's A, B, C. That's the other combination, base Q sub infinity. 4 pieces, we put them together. And let's see if we have covered everything. So AB was the odd height columns, the odd height even width columns that we took away. We took care of that. Now we have already covered this minus A, ABC, AC, and Q, right? So that's it. You just have the dissection. And here's the generating function. So Cilanne-Boulet's theorem for ordinary partitions is proven. Good. What about the distinct partitions? Great. Good timing. I think good timing. No? I don't know when I was supposed to stop. Anyway, so let me finish this and then stop. Anyway, okay, if I want distinct parts, what am I missing? I'm not supposed to have any repetition of rows. Right? I should make sure that the rows do not repeat itself. There's some bijection going on. I'm lying a tiny bit here, but that's okay. You will just need to eliminate the parts that repeat, which is these two factors in the denominator. So multiply with their reciprocals. So you cancel that AC, which is the AC repeating row, cancel that Q, which is the full box repeating row. They're gone. You get the generating function in 4 colors for distinct parts. Cool. So yeah, beautiful theorem, really beautiful theorem, and we will use this to get weighted partition identities from now on. And maybe move on to some other things. We will do some fancy stuff with that, or exotic stuff with that, I should say. All right. Yeah, thank you.